Hello everybody, my name is Kevin, and today we're here to talk about Einstein's special theory of relativity. Number 1. Notion of the inertial frame of reference. First, before we talk about special relativity, let's have a review at what is an inertial frame of reference. When we talk about motion, we must have a frame of reference from which to view and measure the motion. Most often, we choose Earth as our frame of reference, assuming it to be stationary and measuring the motion relative to Earth. Inertia is the resistance of an object to any changes to its velocity, including the magnitude and the direction. It is described in Newton's first law of motion, stating that if an object is at rest or moving in a straight line at constant velocity, it will remain so. So an inertial frame of reference is a frame of reference where the law of inertia holds true. Earth, any object at rest on Earth, or moving in a straight line at constant velocity, are examples of inertial frames of reference. For all these inertial frames of reference, the Newtonian laws of motion hold true. Here, an example. Let's say person A is holding an apple on a bus, and person B is standing on the ground near the bus. The bus then starts moving with a constant velocity in a straight line. If A were to throw the apple straight down, the apple would seem to moving straight down relative to the bus observed by A, or the apple would be seen to move in a parabolic curve relative to the ground observed by B. In both cases, the final velocity of both can be correctly predicted by classical kinematics and their equations depending on the respective frame of reference. Therefore, we see the Newtonian laws of physics hold true to all inertial frames of reference. Now, let's talk about non-inertial frames of reference. An example would be with an apple in a bus. If the bus were to speed up or slow down, the apple would seem to move backwards or forwards respectively. From the point of view of A, who is in the bus relative to the non-inertial frame of the bus, it seems as if there is an invisible force acting on the apple, although in the inertial frame of Earth, the apple is moving at a constant speed. To explain the motion of the apple in the non-inertial frame, based on Newton's laws, we have to invent a fictitious force. In conclusion, we have the following statements about the relative motion and frames of reference. 1. In an inertial frame of reference, an object with no net force acting on it remains at rest or moving in a straight line with a constant speed. Number 2. The laws of Newtonian mechanics are only valid in an inertial frame of reference. Number 3. The laws of Newtonian mechanics apply equally in all inertial frames of reference. In other words, all inertial frames of reference are equivalent as far as adherence to the laws of mechanics is concerned. Number 4. There is no such thing as absolute velocity in Newtonian mechanics. In other words, for two inertial frames moving relative to each other, there is no way to determine which is really moving. Now that we're done talking about inertial and non-inertial frames of reference, let's get on to the special theory of relativity. Many scientists during the 20th century wondered if the speed of light follows vector addition rules. For example, if light has a speed of c relative to Earth, then would light emitted in a forward direction from a source moving relative to Earth at a tenth of c have a speed of 11/10 of c, measured by an observer on Earth? After some experiments by physicists A. Michelson and E.W. Morley, they couldn't find the change in the speed of light relative to their inertial frames of reference. To explain this phenomenon, many scientists offered explanations for this failure of change in velocity. Then, in 1916, a junior patent clerk named Albert Einstein came up with his special theory of relativity. His theory is built upon two postulates. 1. The relativity principle. All the laws of physics are valid in all inertial frames of reference. 2. The constancy of the speed of light. Light travels through an empty space with a speed of c equals 3.00 times 10 to the 8 meters per second, relative to all inertial frames of reference. The first postulate is pretty easy to understand. All laws of physics, including those governing gravitation, electricity, magnetism, and optics, are all the same in all inertial frames of reference. The second is more difficult to understand. To an observer who is moving towards a light source and another observer who is moving away from the same light source, the speed of light is always the same, 3.00 times 10 to the 8 meters per second, regardless of their relative motions. This seems contrary to our common sense, but is confirmed by many experiments and helpful to explain a lot of physical phenomenons. Number 2. Derivation of the time dilation equation. Next, we can talk about time. specifically time dilation. The definition of time dilation is the slowing down of time in a system as seen by an observer in motion relative to the system. Let's explain this with an example. Say there's a spaceship with a person inside, and to make a clock, two mirrors are parallel to each other, and a pulse of light can be emitted from the bottom mirror to the top mirror. When the light leaves the bottom mirror, that's a tick, and when that's returned, it's a tock. If the spaceship was moving with a constant velocity relative to Earth, it would seem as if the pulse of light in the clock was moving straight up then down. So we can let 2 delta Ts to be the time interval separating tick and tock, S being the subscript for stationary and M being for moving. So the time to travel from one mirror to the other would be delta Ts, and the distance between mirrors is c delta Ts. From the observer on Earth, it would take delta Tm for the pulse and c delta Tm for the distance it would seem to travel. Within the time that the pulse moves, the spaceship would move v delta Tm relative to the observer on Earth. Using Pythagoras' theorem, we can then isolate delta Tm and see how it compares with delta Ts. We then divide both sides by c squared, and then we can rearrange the formula to isolate for delta Tm, giving us this shows for any v such that 0 less than v less than c and delta Tm greater than delta Ts. The time interval seen by the earthbound observer moving relative to the mirrors must be greater than the corresponding time interval seen by the observer inside the spaceship, stationary with respect to the mirrors, meaning that time was dilated. The duration of a process, as measured by an observer who sees the process begin and end in the same position, is called the proper time, or actual time, as in delta Ts. The duration that is measured by an observer in two positions with a motion relative to the process is called the dilated time, or relativistic time, as delta Tm. The dilated time is always longer than the actual time. This holds for any clock, and all time is relative to the observer. There is no absolute time. One example to illustrate time dilation is with the traveling twin. Suppose that one twin takes off from Earth and travels to a star and back at a speed approaching the speed of light. The other twin remains on Earth, since the consequences of special theory of relativity only apply in an inertial frame of reference. On Earth, in this example, the twin in the spaceship returns younger than the other twin on Earth. Let's solve a question. A beam of unknown elementary particles travel at a speed of 2 times 10 to the 8 meters per second. Their average lifetime in the beam is measured to be 1.6 times 10 to the 8 seconds. Calculate their average lifetime when at rest. To solve this problem, we first must know what we are looking for. Looking at the question, we are looking for the lifetime of the particle. In addition, we must know what our givens are. We know the speed of light, the speed of the particle, and the average lifespan of the particle. Using the formula we acquired earlier in this section of the video, we know delta Tm equals to delta Ts divided by root 1 minus v squared divided by c squared. So by rearranging our formula to be delta Ts equals to delta Tm times root 1 minus v squared divided by c squared, then substituting our values in, we get the value 1.2 times 10 to the negative 8 meters per second. Number 3. Evidence of time dilation and gamma. The expression is so common in relativity applications that it is given the symbol gamma, so the expression becomes. It is also known as the Lorentz factor, named after the Dutch physicist Hendrik Lorentz. We've talked so much about the theory of time dilation, but is there actual evidence of it? In 1971, 4 very accurate atomic clocks were flown around the world. The hypothesis was that the clocks would have a different time compared to the clock at rest in the US Naval Observatory. Because of the Earth's rotation, the trip around the Earth went around twice, one eastward and the other westward. It was predicted that the time loss for the eastward journey would be 40 give or take 23 nanoseconds and 275 give or take 21 nanoseconds for the westward. Once the round trip was concluded, it was found that the eastward clock was behind 59 give or take 10 nanoseconds and the westward clock was 276 give or take 7 nanoseconds behind. This proved the theory of time dilation to be valid. Another example of time dilation is with muons. Muons are subnuclear particles that are similar to electrons, but with the aspect of being unstable. These subnuclear particles have a lifespan of 2.2 microseconds, but with the usage of the circular accelerator at CERN, Switzerland, the lifespan of the muons were increased to 30 times relative to the Earth. So from reference of the muon, it still lived 2.2 microseconds, but from the reference of the Earth, it lived 66 microseconds. In conclusion, all time is relative to the frame of reference, and such there is no absolute time. Number 4. Simultaneity. Simultaneity is the occurrence of two or more events at the same time. In Newtonian mechanics, there is a universal timescale. On the contrary, Einstein states time is relative, meaning there is no universal timescale, or events that are simultaneous in one inertial frame are not simultaneous in other frames. To illustrate this, let's see the following thought experiment. An observer, S, is stationary in the inertial frame of Earth, and is standing on a railway platform at the midway point between two lamps, L1 and L2. The two lamps are turned on at the same time by one switch. Since observer S is located at the midpoint between the lampposts, the distances the beams of light travels are equal, causing the arrival of the light from the one lamppost to be simultaneous with the arrival of light from the other lamp. Adjacent to observer S is a second observer, observer M, sitting in a train on a straight track next to the platform. If the train was moving with a velocity v relative to Earth, in the time interval it takes for the flash of light to travel to observer S from each lamppost, observer M will have moved a short distance to the right. In this time interval, observer M will receive the flash of light from lamp 2, but not yet receive the flash from lamp 1. Since the light travels at the same speed according to Einstein, observer M will conclude the two lamps are not on simultaneous. So we conclude that two events that are simultaneous in one frame of reference are not in general not simultaneous in a second frame of reference with respect to the first. Therefore, simultaneity is not an absolute concept. Number 5. Length contraction. Once we assume speed of light is constant, and time isn't, it brings up the question if length can be changed based on the frame of reference. Consider a spaceship making a trip from planet A to planet B, at rest with respect to each other, and a distance of length s apart, relative to the planets, and at a speed v, as measured by an observer on either planet. For the captain in the spaceship, the process, the departure of A and to the arrival of B, occurs at one single place, the spaceship. The captain can thus assign a proper time duration, delta ts, to the process, and the distance separating the two events to be length m equals to v delta ts. For observers on the planet, the process occurs at two different places, and ls equals to v delta tm. From the time dilation relationship, we know. So if we multiply both sides by v, we obtain, but Lm equals to v delta ts, and Ls equals to v delta tm. Substituting both in, we obtain, also known as, since root 1 minus v squared divided by c squared is less than 1, and Lm is less than s, Ls is the proper distance or actual length between A and B, which is directly measurable in the inertial frame in which A and B are at rest, and Lm is the relativistic distance deduced from kinematics between A and B, as seen in an inertial frame in which A and B are moving. According to Einstein, the relative length is shorter than the actual length, and length contraction occurs in the direction of motion. Let's solve a question. A spaceship passes you at the speed of 0.90 c. You measure its length to be 50.0 meters. What is its length at rest? To solve this problem, we first must know what we are looking for. Looking at the question, we are looking for the length of the spaceship at rest. In addition, we must know what our givens are. We know the speed of light, the speed of the spaceship, and the length of the ship when it's moving. Using the formula we acquired earlier in this section of the video, we know Lm equals to Ls times root 1 minus v squared divided by c squared. So by rearranging our formula to be Ls equals to Lm divided by root 1 minus v squared divided by c squared, Then substituting our values in, we get Ls equals to 115 meters. Number 6. Relativistic momentum and relativistic kinetic energy. First, let's talk about relativistic momentum. In Newtonian mechanics, momentum is the product of the mass and velocity of an object, and is conserved whenever there is no external net force on a system. According to Einstein, the equation for momentum can be given as P equals mv divided by root 1 minus v squared divided by c squared. Note, v is the speed of the object relative to an observer at rest, and m is the mass of the object measured by an observer at rest relative to the mass. This mass is referred to as the rest mass. Anything traveling greater than 0.1 c can be called relativistic, and significant correction using the special relativity relationships is required. Using the previously shown equation for v as approaches c, an object with non-zero mass p approaches infinity. The unbounded increase of relativistic momentum reflects the fact that no body of non-rest mass can be accelerated from an initial speed less than c to a speed greater to or equal than c. Kinetic energy is defined in Newton's law as the work needed to accelerate an object of a given mass from rest to a stated velocity, while relativistic kinetic energy is the extra energy an object with mass has as a result of its motion. We can find the kinetic energy of an object using Ek equals to E total minus E rest, which then can be substituted into Ek equals to mc squared divided by root 1 minus v squared divided by c squared, and then minus mc squared. Number 7. Mass-energy equivalency. According to Einstein, the total energy is defined as an object with mass m moving at v relative to an inertial frame of reference. If the object is at rest, the energy will be E equals mc squared. He proposed two things. Rest mass is a form of energy that is associated with all massive objects, and there might be forces or interactions in natures that could transform mass into a type of energy, and vice versa. In classical mechanics, mass and energy are conserved separately. On the contrary, in special relativity, these conservation laws are generalized to become one combined law, the conservation of mass-energy, or mass and energy is also interchangeable. Only with the technological advances of the 20th century did physics see mass converted into energy with the achievement of nuclear fission. This led to the making of the atomic bomb. How does special relativity differ from Galilean relativity? And what key paradigms in physics did special relativity shatter? Galileo Galilei was an Italian astronomer, physicist, and engineer. He first described his principle of Galilean relativity in 1632, stating that the laws of motion are the same in all inertial frames of reference. This means there is no absolute velocity, and all velocities are relative to the frames of reference. Einstein's special relativity differs from Galilean relativity by stating that time and length are also relative to the frames of reference, and there is a relationship between mass and energy. Special relativity changes the paradigm of classical physics. This is done because the time and length are no longer absolute measures, but relative to the frames of reference. In addition, mass and energy are not separately conserved, but conserved in a combination. Mass and energy are also transferable between one another. And that's the conclusion on my video for special relativity. I hope you've learned something from this video, and I'll see you next time. Bye!